Welcome everyone to this week's edition of HoloTube. We're very happy to have Romatschke with us. If you're wondering why I'm screen sharing or why something looks a little bit different, we had some technical issues with Zoom, and now Paul is going to tell me when to advance the slides. So this is how we work around, but no matter, we're very happy to have you, Paul. The floor is yours.
Okay, thank you very much. Yeah, I apologize for the technical difficulties here. Okay, so I want to take you on a trip to Wonderland, quantum field theory in Wonderland. And the Wonderland picture that you see over here, that's actually pretty close to here. It's Rocky Mountain National Park in the winter. And you can kind of imagine that the two people here are Matthias Kaminski, who's leading the trail here, blazing through the snow, and a slightly pear-shaped me who is following along. And that's basically how we like to sort of do things here in Colorado. So in order to get started, I wanted to start by basically thanking my group. So please, can you advance the slide to the next? Thank you. Yes, so basically I have to first thank my boys here with who I sort of have a lot of physics discussion here, and who are really sort of very nice and sort of pretending that they learn a lot from me, even though I learn much more from them. So thank you, boys, if you're listening. You are doing a great job, and I'm very happy to work with you. Next slide, please. Okay, I want to get started by some motivation. Next slide, please. And my motivation really stems from trying to understand quantum chromodynamics. So you're very much familiar with plots like these, where we have the QCD running coupling alpha s as a function of the scale. And you can see that the coupling constant decreases as a function of the energy scale. That's a property known as asymptotic freedom. And it's well documented in QCD. It's also well understood. And we have data from different experiments corroborating the theory behind that. Next slide, please. So in QCD, that also works, yeah. So in QCD, basically, we have three different sort of things that we like to understand. One of them is asymptotic freedom, which we understand. Next slide, please. Through perturbation theory. Next slide, please. There's also a property of confinement, which we don't really have a good understanding of. And next slide, please. There's also the property of low energy bound states, which are colorless degrees of freedom, such as pions and protons, hadrons in general. And for those, we basically only have understanding through numerical simulations, such as lattice Monte Carlo simulations. Next slide, please. There are some problems with our tools, in particular when we try to understand properties of quantum chromodynamics that require us to understand regimes where the coupling is large. And those are the regimes where we find confinement and bound states. And clearly, because the coupling is large, we can't use perturbation theory. Next slide, please. So one idea that has cropped up time and time again in the past was that we could try to, instead of solving QCD, which is an SU3 gauge theory, try to solve an SUN gauge theory in the limit of large n, under the assumption that if you have n very large, then 1/n is a small parameter, and you could use that as an expansion parameter that doesn't rely on the coupling, so it would be applicable even to the large coupling regime. So that's a nice idea. Unfortunately, we can't really solve large SUN gauge theories either. Next slide, please. So we have also, in the past 20 years, learned that there are some large gauge theories that can be solved through tools such as holography. And there are indeed some properties that are present in some models, some holographic models that capture some of the properties such as confinement or these bound states. But the problem there is that it's not really QCD from the start. And sometimes it's kind of hard to know which results are coming from the model input, and which results are truly just large coupling properties of an SU-N gauge theory. So the plan for this talk here is that I want to start with reminding you of two ingredients that I'll need. These ingredients are properties of PT-symmetric field theories and how to solve large and scalar field theories. And after I've reviewed those, I will sort of try to take you into Wonderland and talk about what kind of really wonderful things you can do if you sort of put these two things together. So I'll talk about solvable theories with asymptotic freedom and try to sort of take you down the rabbit hole to see what other things we can do with this approach. So let me get started by talking about PT-symmetric field theories. The best way to sort of learn about these PT-symmetric field theories, in my opinion, is to sort of learn from the person who has been instrumental in sort of putting this up. This is Carl Bender. And if you look at the recordings of Carl in the fall 2020 HoloTube Seminar archive, you find a talk on unmasking PT symmetry by Carl, which I recommend very much in trying to understand what this subject is about. Next slide, please. In a very brief way, I want to sort of give you the sort of salient features of what these PT-symmetric field theories are. So first of all, PT stands for parity and time reversal, and PT symmetry is kind of a subset of Hermitian symmetry. So that's what you should be taking away from this. And I want to contrast a normal Hamiltonian, which is written here, for instance, as a normal Hamiltonian for quantum mechanics, with PT-symmetric quantum mechanics. Next slide, please. So you know that if you have Hermitian bounded Hamiltonians, such as the one that you have here on the slide, then the spectrum of eigenenergies of this Hamiltonian is real and positive. That's guaranteed by hermiticity and boundness. So En is larger than 0. By contrast, we can look at a so-called PT-symmetric Hamiltonian. For instance, that's one where the coupling sign is flipped. So I've written it down as minus gx4, or I can equally well write it as ig squared, there's an x missing, igx squared and x squared. And this Hamiltonian is PT-symmetric because if you change p, then you're reversing the sign of x. And if you change the t, then you basically sort of take the complex conjugate. So this Hamiltonian, even though formally it's also Hermitian, is unbounded. And from this point of view, you would sort of say that, oh, wait a moment, this Hamiltonian doesn't give rise to sort of a positive and real eigenspectrum because the potential is sort of unbounded. Or if you put it in terms of igx squared, you would say that, oh, wait a moment, the potential sort of has these i's in there. I don't expect a real eigenspectrum. The big surprise is that the eigenvalues of this Hamiltonian are also real and positive. And this is something that came as a surprise back in the last millennium, and it's been sort of giving rise to a whole lot of further developments as we go on. So this was quantum mechanics. So now we can try to upgrade this to honest to God quantum field theory. So you would write out an action for PT-symmetric quantum field theory by starting with a normal action, such as the one that's given here with the slide. So I'll take 5-4 theory with the usual kinetic term. And if you look at this action, you know that we have a lot of tools to sort of analyze what's happening in this theory. In particular, we know that the action is bounded. The theory is renormalizable. The theory has positive beta function in perturbation theory. And because it has positive beta function, it turns out that this theory is quantum trivial, which means that the sort of interacting, there is no sort of interacting fixed points of this theory. So this is a proof that was given recently, like 2018 or so, for the case of positive coupling constant. Next, yeah, thank you. So by contrast, if you look at the PT-symmetric action, that's the one where I flipped the sign of the coupling constant in the 5-4 term to minus g. then you would normally say that, oh, wait a moment, this is an unbounded action. It's still renormalizable. So if I sort of just close my eyes and renormalize this theory, I find that, oh, wait a moment, because the sign of the coupling is flipped, this theory has negative beta function. So it's asymptotically free. And we can talk about the properties of this theory here. Next slide, please. In particular, there was a very nice paper fairly recently, September of last year, where it was conjectured on how to relate this PT-symmetric field theory to its usual Hermitian cousin. Next slide, please. I refer to this as the so-called ABS conjecture for Eye, Bender, and Sarkar. And the conjecture simply says that if you take your usual Hermitian theory, which is giving you a partition function z at a coupling lambda, and you take lambda to be negative, so lambda to be minus g, then you get access to the PT-symmetric field theory simply by taking the real part of this partition function. Now, next slide, please. That is, of course, a fantastically simple way to get the result for negative valued coupling constant. Next slide, please. But unfortunately, it's also probably wrong for 5-4 theory. So we are still working out the proofs behind this, but it probably doesn't work for 5-4 theory. It's subtle. We'll try to write a paper on this pretty soon. However, the main upshot that I want to give to you is that the statement, this ABS conjecture, can in fact be proven in the larger n limit for scalar quantum field theory. And that's basically what I'll be using. So here's the first lesson. It's clear that Hermitian unbounded action is sufficient for consistent quantum field theory, but maybe it's not necessary. So that means that there could be theories with unbounded potential, maybe a 5-4 theory with negative coupling, that are physically acceptable if certain minimum conditions, such as PT symmetry, are met. And there's a consequence from this, namely that we should not just dismiss theories just because the potential seems unbounded. That wraps up my brief discussion of PT-symmetric field theories. If there are any questions on this topic, please let me know now, because I will go on and talk about a different ingredient, which is solving large n scalar field theories next. Okay, hearing no urgent questions, I want to go ahead and talk about large n field theories. And similar to what I did with the PT-symmetric case, I want to advertise basically what our group here has accomplished in that regard here. So there's a talk by me from the 2020 ICTS conference here. The information is below, and that's a 1 hour like expose of how this sort of new way of doing large n field theories sort of work and what you can do with it. However, next slide, please. I will give you, in a nutshell, the main ingredients in case you don't want to sort of sit through another hour talk of this. The starting point here is a Euclidean field theory action, which I've written down here, and I've taken an n-component scalar field, phi vector, and the interaction is then something like a phi-4 interaction, but really it's just phi vector squared. And because of this particular arrangement, this theory has an additional symmetry, which is an ON vector symmetry. Next slide. It turns out that this theory can be transformed using a so-called Harvard-Strantovich transformation into a different form, where instead of having a partition function as a path integral over the scalar field phi, you write it in terms of an auxiliary field zeta, which is the pair auxiliary field. And then the action that you get from this is nonlinear. It involves the trace over the logarithm of the operator, but this transformation is exact. Next slide, please. And because you have this n in the exponent there, at large n, it turns out that the remaining path integral can be solved using the method of steepest descent. So that at large n, you find that the theory localizes, if you want to use fancy language. And all you have to do is the integral over the Fourier zero mode of this auxiliary field. At the end of the day, you end up with a partition function, or log z, which is given in terms of, well, n, beta v, the volume, and the inverse temperature, and a single function p, which you can recognize to be composed of two terms: the free pressure of a massless or massive scalar field, p free of m, plus an extra term that depends on the coupling, m4/16 lambda. And the only sort of, well, the way that you sort of want to interpret this is that you're sitting at the saddle point of this integral, and that means that the value of this mass parameter in this function p is determined by the condition that dp by dm is 0, so p prime is 0. So it's a very sort of straightforward and mathematically exact construction, and it turns out that it's actually very fruitful, in particular for massless fields in 3 dimensions. 3 dimensions because there are no logarithmic divergences there, so you don't have to renormalize anything, and you can just evaluate the theory directly. For 4 dimensions, I was stuck on this theory for a long time. The reason is that you have positive beta function. Since it's large and exact, this is not a perturbative artifact. You really do have a lambda pole in this theory. And in this talk here, I want to sort of give you the resolution of what's going on in 4 dimensions with these large and big theories, which has taken me a few years to figure out. However, I want to use this opportunity to advertise the results that you can do with this technique in 3 dimensions, just to sort of show you what can be done. There are 2 plots here. One shows the entropy density scaled by the free entropy density on the left-hand side as a function of the coupling. And I want to emphasize this is exactly large n, and it ranges all the way from lambda 0 on the very left of the plot to lambda infinity on the very right on the plot. And you find that the entropy density scaled by the free value goes monotonically from 1 to exactly 4/5 in the large coupling limit of this large n scalar phi theory. And on the right-hand side, I've shown a plot of a transport coefficient, the shear viscosity over the entropy density ratio, that also can be calculated for all values of the coupling. This is again large and exact, and you find that at infinite coupling here, this value stabilizes to a constant of about 0.4 or something like this. So the point is that for 3 dimensions, which is a case where we know that the interacting quantum field theory exists, so you can write down a lattice formulation of this and 2 new parameters. There are lots of interesting results there. You can talk about the so-called interacting CFT in the infrared, and you can actually get results for non-perturbative thermodynamics and transport. And if you are more interested, I've sort of put on 2 preprints there that you can look at if you're interested in these. Next slide, please. So I want to return to 4 dimensions here and tell you first what the problem is, and then secondly, how to solve it. So in 4 dimensions, you do exactly the same thing as I sort of said. You derive the pressure function, which is a combination of the free pressure and this m4/16 lambda term. In this equation here, you see that first term m4/16 lambda, and the rest is just the pressure of a massive scalar field in 4 dimensions in dimensional regularization. So you can clearly see the 1/epsilon there. That's the usual divergence. And it turns out that if you stare at this long enough, and you realize that m here is determined self-consistently, it means that there's only one way that you can renormalize this expression. That is, if the m4/lambda term eats up the m4/epsilon divergence for all values of m, basically. Next slide, please. Whoops, that was back. Forward, please. Yes, thank you. So the theory can be non-perturbatively renormalized. You see that because lambda is not sort of written in power series of lambda r, but it's the inverse of lambda that's having the structure here. And by doing this, you find that that coupling sort of is well, you can work out the running coupling from this form. Next slide, please. And you find that the coupling increases as a function of the scale mu. And because of that, the beta function is positive. Next slide, please. This is the form of the running coupling as a function of the scale. The theory has a lambda pole, which I sort of put at the position big lambda LP. And you can see that indeed sort of the coupling monotonically rises and then diverges at the lambda pole. And I want to point out that this is not a perturbative statement because you're doing large n at the leading large n order. And what that means is that this theory really has a lambda pole. There's nothing you can do about it. So you have to sort of figure out what to do. Next slide, please. Yeah, I talked about the lambda pole. You can actually sort of go ahead and say, well, let me just continue plotting that function. And this is what happens. Above scales above the lambda pole, the coupling reverses sign, becomes negative, and then goes back to 0 asymptotically as you go with the scale to infinity. So I sort of, as I sort of tried to emphasize before, a long time I was stuck about this. So now I want to sort of tell you how to sort of make sense of such a behavior for this theory. And the advertisement is that you get a wonderfully solvable theory with asymptotic freedom. So, okay, we have this coupling. The coupling diverges at a particular scale, becomes negative for the scale larger than the lambda pole. And next slide, please. Traditionally, that would mean that people would say that, okay, this theory is clearly sick. It doesn't have, or it's not a candidate for continuum interacting theory because there's this lambda pole. And people say that, oh, but we can still use it as an effective theory with a cutoff at the lambda pole. And as long as they stay much below the cutoff scale, everything is fine and we can sort of do physics with it. Next slide, please. In this talk, I want to entertain a different perspective. I want to sort of take the result that we get for the coupling constant seriously. And I want to fold in the knowledge from PT-symmetric field theory, which says that negative coupling constants are okay. You can get physically acceptable theories even if the coupling is negative. The way to go, in my opinion, is not to sort of get hung up on the form of the coupling constant, but actually look at observables. So that's what I want to do next. And the big thing that I want to remind you, which you probably all know, but maybe have learned not to sort of remind yourself of, is that the coupling constant alpha s in QCD is not an observable. It depends on this fictitious scale Q, which is basically a function of your randomization procedure. And when I show plots like this and we have experimental data on them, it's not actually alpha s that's really sort of measured, but alpha s is inferred by matching a certain randomization procedure to the experimental data. That's really what's done in producing plots like this. So then if we look at our observable or our sort of ON model here, let's see what we get for observables such as the pressure. So we have here the example of the pressure here. I've renormalized it using this coupling in the first equation in the slide. And if I write in the particular form of the running of the coupling, remember that it is given exactly as these 4 pi over log of lambda over mu, then the form of the pressure in terms of the mass becomes relatively simple. The only scale or the only sort of holdover from the coupling is this lambda LP parameter that appears in the expression. And in particular, I want to bring to your attention, next slide, please, that there is no dependence anymore on this fictitious randomization scale mu. Okay, so that's a requirement from randomization group that good observables do not depend on this fictitious randomization point. So the result here is that the pressure here depends only on this scale lambda p, but not on the randomization scale. You're getting way ahead here. So we have the pressure, and it still depends on this parameter m, that is supposed to be solved self-consistently from this saddle point condition, which I've written down here. Again, no surprise, we get an equation that we have to solve. There's a sum of our Bessel functions here, but okay, you can still sort of think about solving this equation numerically if you want to. The main point that I want to sort of get to is that deep in the infrared, next slide, please, which is about at zero temperature, you can actually solve this equation analytically, and you find it has two solutions. There's one solution which corresponds to a zero mass solution here, and there's a second solution where the mass is square root of E, as in 2.7 something, times the Landau pole scale, lambda LP. Next slide, please. M1 is 0, the zero mass solution that you can recognize as the usual perturbative vacuum. That's the stuff that everybody does. The second scale, where you have a non-vanishing mass, corresponds to a spontaneously generated vacuum expectation value of the field. Next slide, please. So traditionally, people sort of select the perturbative vacuum on the basis that, oh, we have this cutoff theory. This second solution here is very close to the cutoff. Well, it's actually bigger than the cutoff. So we throw it away on the basis that, okay, this is much too close to the cutoff. We can't trust it. Let's just ignore it. Next slide, please. However, I beg to differ. I'm of the opinion that physics tells you which vacuum is the right one. So you can't just pick and choose whatever you want to do. And the way to pick the right vacuum is that if you evaluate the pressure or the negative free energy and choose the solution which has the smaller free energy. So wait a moment, go back. The perturbative vacuum has zero pressure. You can sort of easily see that. And the non-perturbative vacuum has a pressure that's positive. So the free energy is minus the pressure. So what that means is that the perturbative vacuum loses with respect to the non-perturbative vacuum. Next slide, please. So the lesson that I wanted you to take away from this is that the perturbative vacuum is actually unstable for all envelopes. The true vacuum is non-perturbative and has smaller free energy than the perturbative vacuum. Next slide, please. And I believe that this means that much of the literature on the four-dimensional N model is actually wrong, or at least incomplete, including some of my own papers. So let me summarize what I just said so far. We have in the deep infrared two solutions, one with the perturbative M is 0 vacuum and the other one with the non-perturbative vacuum. If we then go away from the deep infrared, for instance, if we heat up the temperature to non-vanishing values, we can numerically track the solution, and we can just check that we have the right vacuum by evaluating the free energy and picking the solution that is the lower free energy. That's the physically stable vacuum. So what you get from this is you get a result for the observable, the pressure, as a function of the temperature. And the next slide is a plot of what you get. So you start at very small temperature and you track the right solution and you get a pressure that sort of looks like this. I've taken out the zero temperature pressure and I've divided by T to the 4. And okay, if you say, fine, that looks reasonable to me. It sort of has the behavior that the pressure rises as a function of the temperature, which for an interacting quantum field theory in nature is something that makes sense, okay? So you don't get any funny values where the pressure sort of dives and becomes negative or does something. I mean, it could be doing anything, but it's actually well-behaved and nice. Next slide, please. So I've talked to you about the far infrared. So now let me talk about the complete opposite behavior, namely the UV, the high energy behavior of the theory. In this case, you look at the saddle point equation and you find that all solutions M, as well as the resulting pressure, are complex. Okay. So remind yourself that if we sort of are on the very high UV value of the theory, that's the regime where the solution of the coupling constant told us that the coupling is actually negative. Okay, we've gone way past the Landau pole, the coupling is negative. So you expect funny behavior in this regime. So traditionally, people throw up and they say, okay, this theory is clearly sick, we can't use it. But next slide, please. We do have our PT-symmetric field theory knowledge, and in particular, we do have the ABS conjecture that says that if you have a regime where the coupling is negative, you are getting the physical pressure by taking the real part. So we're going to use that. Let's see what we get. So remember that we start at very high temperature and we go down in temperature tracking the solution, and that's the red dashed line. And the low temperature, you have the black line that I showed you before, and you find that, oh gee, they actually merge at one point, okay? So you have the behavior that the theory has basically a positive and real pressure for positive solutions M for small temperature. Then there is a certain temperature where the behavior changes. I'll call this the critical temperature TC. And then it flips over to this complex pressure, but you're going to take the real part because you're saying that, okay, this is a PT-symmetric field theory. That's the way that I'm supposed to evaluate physical observables if I have flipped the sign of the coupling. You also note that can you go back one more? At very high temperature, the theory stabilizes and it becomes the free pressure of a single bosonic degree of freedom. That's the pi squared over 90 that I've indicated in the black full line here. So the resulting pressure that you get seems perfectly reasonable. It has all the properties that you would expect from a quantum field theory in 4 dimensions. It has these two phases, the low and the high temperature phase. Next slide, please. You can look at what the property near this TC of the field theory actually are. I've plotted here the entropy density. That's the black full line here. And I've plotted the specific heat in the open blue symbols. And what you can see is that the entropy density has a cusp and the specific heat jumps across this critical temperature TC. And from this, you take away that the theory must have a second order phase transition. Next slide, please. So to summarize, if you look at this 4DON model and you don't make any assumption and you don't throw it out as cutoff theory, you find the following properties. The theory has a Landau pole. The coupling takes on negative values for scales above the Landau pole. Next slide, please. However, even though the coupling constant might seem completely sick, observables such as the pressure, the entropy density, and the specific heat in this model are well-defined, positive definite, and show no sign of unphysical behavior. Next slide, please. You do get a second order phase transition located at this temperature that is kind of the scale separating the positive and the negative coupling behavior, and that's separating your low and your high temperature phase of the theory. Next slide, please. So the main point, and I said this before, but I want to reiterate this because it's important, is that in the high temperature phase, you have a negative coupling constant. Next slide. However, you can view this as a PT-symmetric theory with the positive coupling constant GR, which is just minus lambda. So in the high temperature phase, the PT-symmetric coupling is positive and decreasing. Next slide. So the theory is actually asymptotically free in the ultraviolet. Here's a plot of all these coupling combinations again. The full black line, that's the original coupling lambda mu. I told you that has positive beta function for small values of the scale, then flipped signs above the Landau pole and it becomes negative. And the PT-symmetric coupling, well, it's just minus the original coupling, it basically has the opposite behavior. So what I would entertain as a possibility is that for small values of the scale, you basically follow the full black line to the left of the plot. And then once you're across the Landau pole, you should actually consider it in terms of the PT-symmetric coupling, the dashed red line, which indicates that you have an asymptotically free theory. So basically, the theory is always the same, but if you want to interpret it in terms of positive coupling constants, I think that's a sensible way to interpret what's going on there. Next slide, please. So that's my lesson. The running coupling is not an observable, and observables can be finite and well-defined, even if the coupling diverges, which is the usual definition of a Landau pole. But I mean, we knew this for a long time, okay? So people have been playing with n equals 4 super-EMLs in the strong coupling limit, and observables are perfectly well-defined there, right? Nobody goes and says, oh, wait a moment, everything should be sick because the coupling diverges in n equals 4 super-EMLs. So why should it be any different in scale field theory? The only difference, or main difference, I would say, is that for this ON model, you actually can see around this Landau pole and you access this negative coupling constant regime, which using the ABS conjecture tells you that there are actually two phases in the theory. There's sort of the normal phase and there's sort of the PT-symmetric phase, which corresponds to the low and the high temperature phase of the theory. Next slide, please. So traditionally, of course, people reject theories with a Landau pole also because they say that, oh, wait a minute, close to the Landau pole, all relevant and irrelevant operators turn on, everything becomes jumbled, it becomes very complicated. We cannot qualitatively trust the results if we don't turn on all these operators. Next slide, please. In large N, the nice thing is you can actually test this, okay? So you can add relevant and irrelevant operators, such as a mass term, m squared phi squared, or a phi6 interaction, alpha phi squared cubed. And you can go through the calculations, which are technical but doable at large N. And next slide. What you find is that the traditional view is actually incorrect. So these relevant or irrelevant operators do not change the results qualitatively. You do get sort of changes in the results depending on the size of this renormalized coupling constants, but they don't throw out the picture. You still get well-defined results there. And the sort of results that you got from just marginal operators still hold at large N. Next slide. Of course, one can worry about one-to-one corrections. Next slide. The most interesting, or what I consider one of the most interesting, is that in the low temperature phase, this four-dimensional ON model includes a stable bound state in the infrared. Next slide. You can calculate the mass of the bound state. It's about twice, slightly less than twice the mass of the fundamental, about 3 times the lambda scale. This bound state is a singlet of 2 vectors. So it has sort of, yeah, ON basically sort of gets, there's a singlet over N basically. And I really sort of was very puzzled when I found this and very happy because I really think it's QFD in Wonderland. So you start with a Lagrangian that has ON symmetry, then you look at the low energy behavior and you can actually calculate the scalarless or singlet ON bound state that emerges from the theory Lagrangian. And it's the only such state at large. Next slide, please. So from here on, I'm sort of ready to sort of take you down the rabbit hole and see where we can get with this. But I want to pause here briefly and see whether there are any questions on the topics that I've talked about so far. Okay, so hearing no questions, let me then sort of take you down the rabbit hole. Next slide, please. In the last few minutes of my talk, I want to try and sort of link these findings in this ON model, which we can solve, to QCD, which we cannot solve. Next, I want to talk about what happens if you broaden the discussion out to include other fields, in particular fermionic theories. And then I want to finally speculate about potential sort of experimental consequences that you can get from this. So just as a reminder, QFD has 2 phases, the infrared, which is confined, and the ultraviolet, which is asymptotically free. The running is asymptotically free in the ultraviolet, and I want to contrast this with the ON model. So the ON model has 2 phases. There's the infrared with a bound state, and the ultraviolet, which is asymptotically free if you interpret it in terms of the PT-symmetric conjecture. And the running coupling is asymptotically free in the ultraviolet. The ON model has the property that it has a lambda pole, so the coupling diverges at a scale mu is lambda. By contrast, or similarly maybe, QCD also has a scale where the coupling diverges. That's the MS bar scale. And the MS bar scale can be calculated. So you look up the particle data book and there's a discussion on the MS bar scale, and it's 300 MeV. This scale is something that people don't usually interpret in terms of a diverging coupling constant, because it's sort of in the purview of, okay, this is perturbation theory, but that's basically the parameter you get. And I want to entertain the possibility that, okay, maybe the coupling in QCD actually does diverge at this scale. And if it does, then maybe the two theories are not that dissimilar after all. In order to test this, I want to talk about observables again. So I want to talk about eventually sort of the pressure. And the way that I sort of will view this is that I'll say that, oh, wait a moment, I know that the ON model has this phase transition at a particular temperature, which is related to the scale. So it's square root of E, square root of 2.7 something something times the scale. So I want to plot things for the ON model as well as for the QCD in units of square root of E over the, or square root of E times, I'm sorry, I think this is a typo, square root of E times the scale number. Before I do so, I want to remind you of the property of the running coupling. So I plot the toothed running coupling basically in this plot here. So shown are the PT-symmetric ON coupling. That's the dashed, yellow dashed line here. That's the taking over from the plot that I showed you a little bit earlier. The only difference is that I've divided it by 4 pi. So it's kind of like an alpha parameter for the ON model. And I compare it to perturbative QCD. That's the black full line there. I think this is 3 or 4 loop perturbative QCD with a lambda MS bar scale of 300 MeV, where I've also used the tooth definition that is alpha S times MC. That's what's plotted. And just to show that, okay, maybe this is not completely a perturbative statement, I've put in one data point from lattice QCD that's at a scale of about 1 GeV in momentum, and that's the blue full solid dot there, and sort of shows you that, okay, down to a scale of mu over lambda of about 5, the perturbative running sort of is pretty large, and it's sort of consistent with this. So I want to sort of take the QCD running coupling all the way down to 1, basically. Next slide, please. So that's the promised plot. Here we have the OM pressure plotted in units of square root of E over lambda. And you can sort of see the behavior there. We have the low energy behavior and the higher energy behavior. There's a phase transition at around 1 in these units. And then without any sort of modeling, I'll plot the QCD pressure, also normalized by the Stefan-Boltzmann pressure in these units. And that's the blue dots there, blue symbols there. This is 2+1 flavor QCD SU3 with physical quark masses. And you find that it's actually not that far away. Okay, so without tuning your model at all, you sort of get a behavior of a thermodynamic function, the free energy, which sort of shares not only qualitative features with QCD, but also qualitatively is not that bad of a model. So the QCD phase transition, which doesn't have a phase transition in physical flavor space, the crossover temperature that people report is shown in this full solid line that's vertical here. It's also not that far away from what you would predict from the ON model. So I would claim that, okay, this is reasonably encouraging that maybe taking this ON model as a sort of model for an honest-to-God QCD is not a crazy thing to do. Next slide, please. So in my remaining few minutes, I want to sort of just say what other things are going on. In particular, I already mentioned that the same solution techniques do not only work for scalars, but they also work for fermions, such as n-component fermions in 4 dimensions. And my students, Seth and Max, are working out that properties of these theories. So they are in the final touches of their manuscript, which should appear on the archive server pretty soon. So look out for that. And I want to sort of close my talk by speculating about potential experimental consequences of this. So in the standard model of physics, the only known scalar is the Higgs. The sector where the Higgs is important is the electroweak sector of the standard model. This electroweak sector has 4 coupling parameters. It has the Higgs mass, the Higgs self-coupling, and 2 non-abelian couplings, G and G prime. These are in turn fixed by 4 measurements, such as the fine structure constant, the Weinberg angle, the Z mass, and the Higgs mass. But in Wonderland, quantum field theory doesn't need a Higgs mass. And the reason simply is that I told you before, there's this spontaneously generation of a wave that sort of comes out of the theory on its own. So it's radiative corrections that break the symmetry. So the Higgs mass is not something you put in, you get it out. So it's a prediction of the theory. Because of that, it has 1 less parameter than the standard model. And you calculate the Higgs mass and it either works or it doesn't. So right now, the statement I can say is that I find that at 1 loop, the Higgs mass value is off from the experimental known value of 125 GeV or something. But we are still looking, okay? So this is that the rules of the game are sort of still being developed. This is large N, and then you have the sort of perturbative sector, and the electroweak sort of theory is, it's a mess. There are lots of stuff and loops in there. So I wouldn't be confident to sort of say that this doesn't work for sure. At the end of the day, I think I want to sort of write up whatever the result will be, but there will be a value for the Higgs mass in this QFD version of the electroweak sector, and it either matches or it doesn't. But at least it's experimentally, there's an experimental consequence of this. And with this, I want to thank you for your attention. Last slide, please. I'm off to enjoy QFD in Wonderland, and I'm happy to take questions in case you have.
Thank you very much for this very enjoyable talk. And are there questions from the audience?
I have a question.
Please.
So with these PT-symmetric theories, does this lead to unitary time evolution?
Good question. I think it does, but it's complicated because, okay, so if you go back to quantum mechanics, PT-symmetric quantum mechanics, the reason that this works is that you don't quantize on the real axis, you quantize on the complex hyperbolas, basically. So, eventually, sort of, I want to give you a sort of sensible answer in sort of saying that, okay, so this is basically what you get for your unitary time evolution. At the moment, I don't really understand it that well. I'm still learning the rules of the game. What I can say is that for the case of PT-symmetric quantum mechanics, there is a transformation that lets you transform your PT-symmetric Hamiltonian to a Hermitian Hamiltonian, but the transformation is non-unitary.
Okay.
Yeah.
Got it. Okay, thank you.
Sure.
Thanks for the question. Any more questions?
Yeah, I might have one more on that. So if at least in the quantum mechanics non-Hermitian theories, there is this Dyson map that, as you said, maps you to Hermitian Hamiltonian. So if you here are always looking at the PT-symmetric phase, I mean, how does that match with? Wouldn't you be able to rotate all your observables and just to the Hermitian case?
Yeah, it's not quite that simple. So it's not only the observables that are rotated. It's basically sort of the whole coordinates that are rotated. So literally, okay. So for quantum mechanics again, when you try to quantize your PT-symmetric Hamiltonian on the real line, it doesn't work. So basically what you do is you sort of make the coordinate x complex, and you end up quantizing on these sort of complex cones. So it's both the observables, and so yeah, I feel not really qualified to sort of fully answer that. I really sort of recommend looking at Carl Bender's talk on the PT-symmetric aspects of this. So.
Okay, thanks.
Sure.
Are there other questions? Maybe what people think. So these are exciting properties of these PT-symmetric Hamiltonians and theories that that you pointed out. Is there something exciting for holography in this, do you think? And like, do you see a direction?
I mean, I think it's possible. I mean, you know that in particular for the three-dimensional ON model, there's a conjectured holographic dual, namely higher spin gravity in 4 dimensions. But it's undoubtedly much richer than the usual holographic sort of principle. I mean, you can already sort of see in 4 dimensions, you have these 2 phases. So whatever is going on the holography side is going to be very rich. That's for sure. So.
Any problem that one could tackle? I mean, the idea, I mean, one major thing is also finite coupling corrections, and that one would want to understand better in holography, right? Even just qualitatively. And it seems like that could be something that with these PT symmetric approaches one could get a hold of.
Yes, but let me sort of, okay, I mean, I don't want to sort of dampen the enthusiasm of doing that with the PT symmetric ones, but I think that if you were to be interested in finite coupling corrections in holography, I think the much more, it's not low hanging, but the easier task is to look at the 4-dimensional gravity dual to 3-dimensional ON theories, because that theory at least doesn't have these 2 phases, and it still has finite coupling corrections, but it's a 4-dimensional gravity theory. It's still higher spin, but at least they're not these 2 phases, and it's much less complicated than the 5D gravity theory that could be dual to these PT-symmetric 4-dimensional ON models. Mm-hmm. That's my take on it. So I think that there's sort of interesting things to do in any case, but the easier task is the 4-dimensional gravity theory dual to 3D ON models.
Okay, thank you.
Sure.
Any more questions? I don't see any, so then thank you very much again, Paul, for this very nice and enjoyable talk. And thanks everyone for the questions, and I'll see you again next week.
Thank you.